So thank you to the organizers for allowing me to speak remotely. I do appreciate that courtesy on this paper I published last year. A little bit about me. If anyone wants a copy of the paper or any other papers in this presentation or the presentation, just email me and I'll be glad to send it to you. I have an electrical engineering background, was a research scientist at Westinghouse and the Nuclear Regulatory Commission, and I've been a patent attorney for the last 30 years. And my second job is to do the research into the quantum biology of ferritin since 2017. So the title of my paper might raise some questions. One could be, does ferritin interact with microtubules in vivo, and what is the evidence of that? Well, first, some basics. Ferritin is a protein complex that forms from 24 subunits. They self-assemble into a hollow sphere that's called apoferritin. But in the labile iron pool, it starts to store iron almost as immediately and becomes holoferritin, which contains iron. Almost every living cell has ferritin, from thousands to hundreds of thousands of ferritin particles, depending on the cell. This electron microscope image shows how difficult it is to see ferritin in this kind of data. In this study, they tagged ferritin and gold nanoparticles to microtubules. And you can barely tell the difference between the ferritin and the nanoparticles. And that's because you know they're there. If they haven't been tagged, if they're just endogenous ferritin particles, they could look like other stuff in the cell. So it can be difficult to use electron microscopes in vivo. Hassan et al. Looked at the association between ferritin and microtubules in vitro, and they have this electron microscope data that shows a pretty clear association between the two. Now, of course, this is in vitro. It's not a cellular environment, so it's going to be artificial, but you're going to need more evidence. You know, what fact have we proven with this study? Well, I think we've proven that microtubules and ferritin will interact in vitro. There's different burdens of proof in court, from preponderance of the evidence to reasonable doubt. I think for scientists, we want to endeavor to get scientific proof, which is repeated tests at different unaffiliated labs. So this one test from Hassan et al. Is not that. Hassan et al. Next year published this paper where they looked in vivo, and they used fluorescent markers at a higher, lower resolution, higher area. And you can see the microtubules over here. I hope you can see my cursor. And then the ferritin here. They look very similar, but there are no microtubules in this image data, and there's no ferritin in this. So the similarity, I think, indicates overlap between the two. They have the merge image. This is in a fibroblast cell. This is from a hepatoma cell. And you see the same extensive ferritin and microtubules overlapping. They did other tests also and concluded that a significant fraction of ferritin molecules coexist with microtubules. So this is one in vivo test and one in vitro test. And you really have to read this paper to understand what it has and its limitations. This is a second in vivo test by a different group, which used the same type of fluorescent markers to look at chicken erythrocytes and human platelets. Here's the indication of correlation between ferritin and tubulin in the erythrocytes. They added horse spleen ferritin, which is a very common type of ferritin to use, and duplicated those results. And here's the human platelet data. So now we have two in vivo, one in vitro. Here's a third in vivo study that used a knockdown of the ferritin heavy chain gene, and that induced microtubule collapse. So it seems that ferritin is necessary for microtubules not to collapse. When they enforced expression of that gene, the microtubule function for erythroid differentiation was restored. So I think, based on this evidence, that we can say to a scientific level of certainty that ferritin is interacting with microtubules in vivo. So it could be very important for microtubule studies. Next, does ferritin quench microtubule fluorescence, which would be important for those studies that are looking at that aspect of microtubules. I only found one study on that, and that is this Ghosh et al. Study. And they were looking at using apoferritin, that's the ferritin without anything in it, as a carrier for anti-cancer drugs. But they did this one additional study where they measured the effect of apoferritin on tubulin, and they showed pretty good evidence of quenching. I note that it was quenching at 295 excitation from 310 to 400 nanometers. You can see the quenching is all across that wavelength area. So when you look at other data, like this study from Al-Bailey et al., it looks like apoferritin can absorb photons up to about 330 nanometers. So when you're combining it with microtubules in that one in vitro study, again, recognizing the limitations of in vitro studies, how they're not real cellular environments, it looks like you could extend the effectiveness of apoferritin in quenching microtubule fluorescence. This is the curve for holoferritin with iron in it, and you see it's much better at absorbing photons, going up to over 561 nanometers. Here's 488, and I flagged those because the rest of the Ghosh study was looking in vivo. And in this set of data, you see fluorescence data in a control. You can see microtubules in this image, and they're very faint. We don't know a lot about how they generated the image data, the intensity of the laser or what have you, but they were testing it versus docetaxel, which is a microtubule stabilizer, as luck would have it, but that causes cells to die. You think microtubules have to be stable, but they actually have to dynamically change in response to the cellular environment. And this shows that the cells are starting to die off. The microtubule networks would not be affected by the docetaxel. Here we have apoferritin and docetaxel. And it's a marked difference in fluorescence. But is that due to the apoferritin being an effective carrier, or is it the apoferritin contributing? We don't know, because apoferritin and microtubules in vivo is an uncontrolled variable. And this is why uncontrolled variables are bad. They affect your ability to make any conclusions as to that point. Now, Ghosh was looking at using apoferritin as a carrier, and that was what they were concerned about. They showed that it was slightly more effective at reducing cancer cell viability, probably not enough to account for the difference in fluorescence. So I think there's some evidence, preponderance of the evidence, some level of evidence that apoferritin is quenching fluorescence in vivo. Also, I note that when apoferritin dumps the contents that it's been loaded with, it's going to start storing iron, so that we could be looking at holoferritin effects. But in any event, this is the only study that kind of looked at it, and I think it really needs to be looked at more. There's also this data which shows quenching of tubulin fluorescence in response to UV excitation with increasing magnetite nanoparticles being added. And this is relevant because I think ferritin could potentially have magnetic field effects like magnetite, and I'll show you that in a moment. So does ferritin quench microtubule fluorescence? I think yes, at least in vitro, which is where a lot of microtubule tests are done, and possibly even in vivo. Now, does ferritin have biophotonic, bioelectric, and biomagnetic properties that could interact with excitonic energy transport through microtubules? And again, yes, we've seen how ferritin can absorb UV. What it does with that absorbed energy is it stores it as electrons in the core. And that was shown in this study, which I highly recommend. They compared it with electron beam loading. So it's a pretty good study that shows that ferritin acts like a nanobattery. This study by Christian Nijhuis and his colleagues is one of many. There's others also by other researchers that show electron tunneling through ferritin. This one is very thorough, but basically if electrons are being stored in the core, they could conceivably tunnel out to neutralize ROS, say, which is a function that has been observed many, many times in medical studies, that ferritin overexpression in response to ROS and ferritin acting like an antioxidant is a biological observation. In this study by Professor Ron Nauman, who is one of the people who identified chiral-induced spin selectivity, his group looked at the interaction between chiral molecules and 10 nanometer superparamagnetic nanoparticles. And he found that those chiral molecules and the electrons and protons transferring through them can imprint ferromagnetism on the superparamagnetic particle. He measured up to 80 Orsteds of remnant flux, which is a pretty big level of flux for a small particle like that. So if something like that is going on with ferritin, what could it mean? Well, what's operative is the Kelvin force. due to a B field gradient from a small particle. And for a 12 nanometer particle with 8 millitesla of flux, which would correspond to 80 Oersteds in free space, I calculated that Kelvin force is 10 to the minus 17th newtons, which sounds very small, but if you consider how fast it would accelerate an electron and the distance that the electron could travel in a nanosecond, at the surface of ferritin, that force is enough to move it 20 microns, the electron, 2 nanometers, 6.5 microns, at 5 nanometers, 1.8 microns. Now, obviously, electrons aren't going to move that far when they're 5 nanometers from the surface of a ferritin particle, but electrons would be paramagnetic and would be attracted to a magnetic field, and other ions would likely be paramagnetic also, such as ROS and antioxidants. So based on that and a bunch of other data, I tried to create a model for the bioelectric and biomagnetic properties of ferritin, because people just think of it as a particle that's like an iron oxide nanoparticle, but it's actually more like a nanomachine that's very complicated. This is a very basic model because it shows ferrohydrite taking up the entire space in the core, and actually the data shows that this is a very rare situation for ferritin. Usually it has less than a full core, and it has multiple nanoparticles in it. I also have this magnetic model that shows antioxidants being attracted, paramagnetic antioxidants to paramagnetic to the ferritin and donating their electrons, and then the ROS being attracted and receiving the electrons, again, explaining what's been observed in many studies that ferritin is overexpressed in response to ROS and inflammation. I also note that this paper did discuss, and an earlier paper discussed, how ferritin could be associated with magnetosensation, and it has a calcium-iron neuronal signaling connection. I don't have time to really go into that, but it's predicted this very recent study last week that dropped that showed that homing pigeon navigation relies on superparamagnetic macrophages. And again, it needs to be studied more, but it's certainly fertile ground for study. So I would say, yes, ferritin has these biophysical properties that could make it an important quantum biological factor. So in conclusion, rather than forming a cytoexcitonic framework, as some people have suggested that this solves all the problems with issues that you can't address, the evidence shows that in fact ferritin quenches microtubule fluorescence and has properties that could interact with excitonic energy transfer. And you really have to consider it not just for microtubule studies, but really for all quantum biology studies. Ferritin is prevalent in cells. It's in the mitochondria, and it could be adjacent to the mitochondrial electron transport chain. It's in other cellular structures. So I would encourage you to at least consider ferritin in your experiment designs and studies. In other words, there's a ferritin-sized hole in quantum biology, and it needs to be filled with further research. So thank you.